The reason why we can use blackbody emission to model, explore, and extract information from stars is because stars are not perfect blackbodies, but they're quite close to it. To demonstrate this in reality, what I've done here in this Python plot is to place our sun. This is the sun's spectrum. Remember, spectra will be given in units of flux density, so that's flux per wavelength. In this case, I'm using in the x-axis nanometers. Hopefully you won't be confused. And all I did is I took the sun to be at 600 parsec away. If you remember, if you take a source further away, then its flux will go down as 1 over distance squared. Now what I'm comparing here is the spectrum of the sun with different black bodies. They're perfect black bodies because they're using Planck's function. What you'll be able to notice is that specifically this black body with a temperature of 5,700 Kelvin is actually really close to the sun. So I've also placed these black bodies at 600 parsec away so that there is a direct comparison. But you'll see that if you put a black body with a higher temperature of 6,000 Kelvin, it starts to deviate significantly from the sun spectrum. And if you put something that's much colder, it also deviates, but on the other direction. Of course, you can say that even though this is not a very bad approximation, and this is also not the exact surface temperature of the sun, so there's some wiggle room there. The important thing that you might be able to notice is that specifically at the shorter wavelengths, there are some gaps between what you would expect from a perfect black body and the sun. The reason for it is actually because the sun, on top of being sort of a black body, also has a lot of absorption features that come from heavy elements actually absorbing some of the energy. So even though the sun's emission is pretty much like a black body, what you have on top of it are absorption features from elements that will actually be capturing that light and making it deviate from a black body. In real life, we don't really have access to spectra of all stars or galaxies, and therefore this is one of the big reasons why astronomers started using colors, and we've seen that a color is a difference in magnitude, such as, for example, B minus V or B minus R that you can see here. If we think about stars as black bodies, we can very simply realize why actually calculating a color will give us some sort of proxy for temperature. And the reason for this is captured here. A very quick recap of what we've covered in section 4. A color, or a difference in magnitudes, is really just about looking at the ratio of fluxes from two different bands. And what we can very easily see, actually, is that if we compare the curve of, say, a 8,000 Kelvin blackbody with a curve from a 6,000 Kelvin blackbody, and if we compare the fluxes at around, say, 4,000 angstroms or 400 nanometers versus something in the red, say around 700 nanometers, we'll see that the ratio of fluxes is going to be very different. Therefore, we can calibrate empirically, or in a more quantitative way, we can calibrate how a color for specific filters corresponds to a specific temperature. And this is what astronomers then use. As a specific example, I've just produced the same exact plot, but then showing what we're actually doing when we're calculating, in this case, B minus R colors. What you can do is, if you take a black body, this is given analytically, it is very easy. And for the specific black bodies, what you can do is actually integrate the curve within the limits given by the B band in this case, and the R band in this case. If you do that, you can get the magnitude. It's sort of an artificial magnitude of what the perfect black body would have. But the important thing is you can then compare colors. What is shown here is essentially the product, the result of doing that. For an 8,000 Kelvin black body, the B minus R color will be minus 0.63. Remember that when we talked about negative colors, we said that they would be blue. For 6,000 Kelvin, the B minus R color is minus 0.2, so it'll still be blue, but not as blue. And for 4,000 Kelvin black body, this color becomes almost 0.7, and it's higher than 0, so we would say that this is red. What you can do is, for example, fit a linear relation between the color and the temperature to derive something like what I have here that you can very easily use, for example, even in the first worksheet. This means that if you calculate the B minus R color, then you can actually calculate the temperature of that source, provided it is very well approximated by a black body. What this also implies, obviously, is that in general, sources that have red colors are colder than those having blue colors. And sources that are very, very blue are incredibly hot. Those that are very, very red are very cold. And you can see this demonstrated for this specific color, but it will be valid for other colors as well. We will come back to this aspect, but I think it is already good to start looking ahead when we talk about galaxies, but also when we look at a specific object in astronomy at different wavelengths, because at different wavelengths, you're seeing different temperatures. Then in an object like a galaxy that's just behind me, when you look at the highest temperatures, like here, versus looking at temperatures which are almost the human kind of temperature that emits at 9 micron, you are seeing a completely different morphology because you're seeing very different physics. We'll see that in this case, we're looking at the smallest, least massive stars versus when we look at the shortest wavelengths where we're seeing the hottest, in this case, the hottest stars, which are the short-lived ones that are incredibly massive. But we will come back to this.